Hello and welcome to the Chemistry Academy. In this video we are going to be going over molecular orbitals in relation to the Advanced Higher Chemistry course. I am super excited for this one because this is my first tutorial with my new camera, so hopefully you guys appreciate the new quality and it'll make it easier to see my scribbles on the board, although it's probably going to make me look more my age. So anyway, pros and cons. As long as you guys can see the notes better, that's all that matters. So let's get into it. So molecular orbitals is one of these topics that you'll cover when you do organic chemistry, and it is one of the topics that does tend to confuse people, but it's actually quite straightforward when you get your head around it, and it's actually very similar to atomic orbitals that you did in Unit 1 when you did quantum numbers and everything like that. So basically, molecular orbitals get formed when atomic orbitals combine in order to form bonds. And so that's why they get called molecular orbitals, because you would find them in molecules, because it's where atoms have joined with each other in order to form a covalent bond. So for every two atomic orbitals that combine, you form two molecular orbitals. Okay, so no orbitals are lost in the forming of molecules, they just combine and form molecular orbitals instead of being classed as atomic ones. So the two molecular orbitals that are made, one's called a bonding orbital and the other one is called an anti-bonding molecular orbital. You might notice I've got a little asterisk here. That's because the anti-bonding orbitals are notated as the asterisk. That tells you it's the anti-bonding one. So if we look at this example here, the two hydrogen atoms, they're atomic orbitals, 1s orbitals. Those 1s orbitals combine to form a bonding molecular orbital and an anti-bonding molecular orbital. The anti-bonding orbitals are higher in energy than the bonding ones, and when it comes to populating electrons into these molecular orbital diagrams, you occupy them in order of increasing energy, which is very similar to what you did in the atomic orbitals stuff when you were doing electron configuration. Okay, so it really is just the same sort of situation. However, when it comes to atomic orbitals, you would have done your box notation going horizontally across the page. When it comes to molecular orbital diagrams, the molecular orbitals get stacked vertically instead, but in terms of populating electrons into it, it's just the same process. Say we had two helium atoms here. In a helium atom's 1s orbital, there are two electrons. So if the two helium atoms combined, we would have two electrons in the bonding and two electrons in the anti-bonding. Okay, so if I just quickly change this to suit. So again, the electrons pair with opposite spins, just like the Pauli exclusion principle in atomic orbitals. And yeah, all the electrons that have come from the atoms end up in the molecular orbitals. So because we've got two in each, we've got 4 electrons altogether. So 1, 2, 3, 4. And they occupy the molecular orbitals in order of increasing energy with opposite spins once they get paired up. So that's really how it's kind of similar to atomic orbitals. Let me just fix this diagram. So if you are given a molecular orbital diagram to populate with electrons, just look to see how many electrons your atoms have, and then just make sure you use up all the electrons occupying the levels in order of increasing energy. You won't be asked to, it's very unlikely that you'll be asked to draw one of these molecular orbital diagrams from scratch. So as long as you can populate one or read one, like interpret one in terms of identifying which are the bonding orbitals, which are the anti-bonding orbitals, that's all you really need to do. So anti-bonding orbitals are the one with the asterisks, the bonding ones are the ones without the asterisks. In terms of what this looks like on like a electron density level, the bonding orbitals is where the orbitals have overlapped and they are sharing electron density, so they're actually sharing a pair of electrons. Whereas in the anti-bonding orbitals, the electron density is not being shared, which is why it's not creating a bond. As far as what the bonding and anti-bonding means, that's all you really need to know, is that in the bonding or molecular orbitals, the shared pair of electrons are being shared. In the anti-bonding molecular orbitals, the shared pair of electrons is not being shared. Okay, But it'll be very unlikely you'll see a diagram like that anyway in your exam. It's mostly these ones that you see. So hopefully that helps you give you a bit of background onto what molecular orbitals are. Like I said, they are very similar to atomic orbitals. It's just when atomic orbitals overlap and combine, they form molecular orbitals instead. For every atomic orbital you get one molecular orbital being formed. So, and then you end up with one being a bonding one and one being an anti-bonding one. So then if we talk about the ways that these orbitals overlap, and this brings us on to sigma and pi. So sigma and pi are two types of covalent bonds that you will come across in the advanced higher chemistry course. And the Greek symbols that represent them, everyone's usually familiar with pi because of maths. The sigma is this circle with a wee sticky outline. So there are two different types of atomic orbital overlap that leads to different types of bonding. So they're both type covalent bonds. It's just the strength of those bonds is slightly different, as you might have noticed over there already. So if the orbitals overlap end-on, so that's the phrase you kind of want to remember, it's end-on overlap. The other thing that they might say in the exam is that it's along the axis of a bond. So basically if the axis of the bond is here, then the orbitals are overlapping along that axis. So for s orbitals, s atomic orbitals, that's the only way that they can overlap because they're spherical. So if you have two atoms with both that have their outer orbital as a 1s or a 2s, then they can only form one sigma bond. That's it. That's all they're going to be able to do. Okay, just remember I'm referring to the outer atomic orbitals, or the highest energy occupied atomic orbitals, because it's the outer electrons that are always involved in the bonding. So any of the electrons inside are not going to be involved. So when it comes to like the bonding of an oxygen atom, that's in the p block, which means it'll just be the p orbitals, the p atomic orbitals that'll be participating or involved in the bonding. Okay, so for two hydrogen atoms, they've only got one s orbitals, so when they combine, they can only combine end on, and that creates your sigma bond. Okay, when you get to like the p block, if atoms in the p block form a bond, then it's going to be the p orbitals that are involved in the bonding, and an end on overlap of p orbitals looks like that. So this would be where, in this example here, this is where the atoms have the same electronegativity. So the electron density is going to be equally shared around the two nuclei. That's what these wee dots are here. If you have a polar covalent bond, which is the case in this fluorine to boron bond, fluorine is much more electronegative, so the electron density involved in the bond is going to be pulled more across to the fluorine side. Okay, so if you see the electron density being unevenly distributed in a sharing electron density diagram, then that means it's a polar covalent bond, because one atom's attracting more electron density within the bonding than the other. Okay, so all you really need to know is what a diagram of the end-on overlap looks like for these two types of orbitals. Don't worry about the d, you're not going to be asked about sigma bonds and d orbitals. So sigma bonds, end-on overlap, and these are what the overlaps look like. Okay. Then if we look at the pi, so the pi, rather than being end-on, is side-on overlap of the orbitals. Now this can't happen for s orbitals, like I've already mentioned, because they're spherical, so they don't technically have an end or a side, they just have a circle. But with the p orbitals, you can get side-on overlap. So this is what they look like. I always think of like the two fat ladies, 88 and bingo calling, that's how I remember it. And it kind of does look like the shape of a pi symbol, or pi, yeah, so it's kind of more relatable. With the sigma, there's like a straight line coming out of it, which can also remind you that they're overlapping in a straight line. But when they combine, basically what happens is the electron densities hover above the two nuclei. So sometimes you will get pi bonding, like, or pi electron clouds, if you like, being shown like that, just so you're aware. But when we're drawing diagrams in the exam, if we're asked, it would normally be this one that we draw to show how they overlap. the pi bonding is not as strong as sigma bonding. As you can probably maybe see from the diagram, the overlap is not as intense. So they are easy to break, which is why you don't need as much energy if you're breaking a double bond or a pi bond instead of a sigma bond. The reason I mentioned double bond is because pi bonding occurs when you've got a double or a triple bond. So the way I like to think of it is the first bond that's formed between any two atoms will be a sigma bond. Okay, so they have to form that sigma bond first. Then, if they're forming consecutive bonds after that, then they will be pi bonds in nature. Okay, so you'll get one sigma overlap, and then any bonds, additional bonds that are made between two atoms on top of that will be pi. Okay, the phrase you also want to remember for if it's pi bonding with a side-on overlap is that it will be classed as being perpendicular to the axis of the bond. So that means because your bond, I'll draw a wee diagram here. So if we have a carbon double bonded to a carbon, so the first bond's a sigma bond, so that would be a sigma overlap, and then the next bond that's formed is then the pi bond. So this is the axis of the bond. The pi overlap is perpendicular to that because they're overlapping in this direction. So they would be overlapping like this. Sorry, I'm not very good at drawing these diagrams. You think I'd be better at them by now. So yeah, the pi overlap is in that direction, so it's perpendicular, i.e. at a right angle to the bond. Okay, so then just some other tips on, and again you just need to know how to draw this diagram, what type of overlap is responsible for the creation of a pi bond. So this is like my little summary table that helps with remembering kind of all the way this all ties together in terms of then the structure of the molecule. So if you have two atoms that are bonded with just a single bond, then that means there is one sigma bond there, okay? If you have two atoms that are joined via a double bond, it means you've got one sigma bond and then one pi bond. If you have two atoms that are bonded with a triple bond, then you have one sigma bond and two pi bonds. So like I'd said before, I always think about the first bond that's formed between two atoms as being the sigma one, and then any consecutive bonds after that are the pi bonds. One thing you'll quite often be asked to do in your advanced chemistry exam is count the number of sigma and pi bonds from a skeletal structure. If you're needing help with skeletal structures, then I do have a tutorial video on that as well. You can go and check out in my advanced chemistry playlist. But we'll do a couple of examples here just now. My tip for this is the sigma bonds between carbon and hydrogen also count as sigma bonds. So in the skeletal structure, the hydrogens aren't shown, but I would advise drawing them on because it just helps you not miss any out. So a benzene ring, remember there's one hydrogen on each point, except for if there's something attached to it. So that's the hydrogens we put in there. Then this carbon here has made two bonds, so it's going to have two hydrogens on it. This carbon here will have one hydrogen, this one will have three, and then there's no other hydrogens to draw on there because that hydrogen is already shown. So if we count the sigma bonds, and when you're doing this, it's a good idea to score out the bonds as you go so you don't end up round in circles or miss one out. So if we do the hydrogen to carbon bonds first, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then I'll go to the carbon and carbon to carbon ones. So 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We've got one there, 21, 22, 23. So we should have 23 sigma bonds there in that molecule. Then if we go to the pi ones, so this is where your benzene ring being shown with the pi electron cloud as a circle is not very helpful. So if it is like that in your exam, which it quite often is, make sure you just draw in some alternating double bonds just to keep yourself right. Okay, so if we're counting the number of pi bonds, then we've got 1, 2, 3, and then this double bond here will be 4. Okay, so like I said, for every single, the first bond between two atoms, that's counted as a sigma bond. Any double or triple bonds on top of that get added to your pi tally. we do the next one, so again add on the hydrogens, so there'll be 2 hydrogens on this one, 1 hydrogen on here, 1 hydrogen on here, 1 hydrogen on here, 2 hydrogens on here, none on there, 2 on here, and then there won't be any on that one either. So if we do our sigma count, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've got 18 sigma bonds there. And then if we go to our pi count, so we've got a double bond here, so that's 1, 2, 3, and then here we've got a triple bond, so that's 4, 5, because remember a triple bond is made up of a sigma and 2 pi, so that's 5 pi bonds altogether. Okay, and that's the sort of thing that you will be asked to do in your exam. So that's my introduction and top tips on molecular orbitals. If you found this useful, please give it a like. Don't forget to subscribe, and I'll see you again soon.